Hello, this is the final presentation for our petroleum engineering research project titled Machine Learning for Well Test Analysis. This project entails developing machine learning models for well test analysis in reservoirs depleted by horizontal wells. My name is Johnstone Omundi. My research partner is Roni Ali, and our project is supervised by Professor Salam. Welcome. On this slide is shown the outline of our presentation. To start with, I will do a quick recap as well as summary and objective of what this project is all about. And then I will introduce a pressure distribution for vertical wells as well as the accompanying model. And then I will introduce the main machine learning model for our study as well as accompanying parameters. And towards the end of our presentation, we will show you the model behavior based on what we've done so far, as well as explain our future plans concerning this study and this project. Well test analysis is one of the tools used for reservoir characterization in the oil and gas industry. Conventionally, bottom hole pressure is recorded against time at constant flow rate. Careful analysis of pressure behavior with time intervals is done, after which reservoir characterization is conducted. This process can be very hectic. The conventional method can be very hectic, in terms of time, the time it takes. Also, it can be very costly because it's a long process and it consumes a lot of money. The aim of our project is to come up with algorithms, with models that can do all this process, automatically. This means our project is going to be more accurate. It will take a much faster time. It will be a cheaper method, a cheaper solution to the conventional method. The first part of our research focuses on pressure distribution for vertical wells. And on the diagrams shown on the slide is the coordinates of our vertical wells. The first part shows X, Y, and H, as we shall see in the next few slides how we apply these coordinates. And the diagram on the right is the top view, the location of our wells. On the slide is also shown the mathematical model to generate dimensionless pressure. We needed to simulate some form of pressure values, PD, dimensionless pressure values, since we do not have real field data to use for our machine learning model. Some assumptions have been taken into consideration. For instance, gassy flow has been assumed. Secondly, we assume at any given time there exists only single phase flow. Finally, reservoirs are assumed to be heterogeneous and characterized by permanent anisotropy. For convenience, we assume the values shown on the slide for parameters used for this study. For instance, Q is 1000 STB per day. Oil formation volume factor is 1.15. Viscosity is 1 centipoise, and so on and so forth. This slide shows the main model we shall use for this study. Our main model is of nonlinear nature and it's a function of pressure and time. P measured or measured pressure should actually be real field data, but since we do not have that at the moment, we simulated our pressure as you saw in the last few slides. P predicted is a function of three parameters, that is alpha, lambda, and beta, as we shall explain in the next few slides. One of the main challenging tasks of this study was to find the three parameters alpha, beta, and lambda, making up the second part of our main model, that is our P predicted. These three parameters are determined using numerical means, and one of the most commonly used methods is the iterative method, also known as the trial and error method. Another method we used is the least square method. In Python, this is known as optimization stroke minimization, and we shall see this in the next couple of slides. The first method we used in the determination of the three parameters alpha, beta, and lambda is optimization stroke minimization function in Python. Our first step, since we do not have any data, is to assume dimensionless time, which we use to obtain dimensionless pressure, PD. From these dimensionless values of pressure and time, we obtain real time and real pressure, or delta P. Using the optimize minimize function in Python, we obtain the three parameters alpha, beta, and lambda. The code that we developed in Python for the determination of alpha, beta, and lambda shall be attached in the report following this presentation. The first screenshot on this slide shows a cutout of the function we used for our optimization and minimization in Python. On the right side, or the second screenshot, shows the results of the optimization function. As shown, the values for alpha, beta, and lambda are approximately 4.1, 3.2, and 3.3, respectively. As you can remember, in the last couple of slides, we showed you the main model used for our machine learning procedure. We use this model to determine dimensionless time, dimensionless pressure, or simulated pressure in this case, since we do not have P measured. And then we were able to determine real time, real pressure, all from this one code, which shall also be shown in the report following this presentation. This slide shows plots of results taken from our optimize/minimize method. The first plot on the top is a log-log plot of delta P derivative versus T. The second one on the right is a semi-log plot of delta P versus T. The third plot is shows a log-log plot of dimensionless time against dimensionless pressure. In the next few slides, my research partner Roni will explain the second method and compare results yielded from the first method, that is the optimize method, and the second method used, which is try and error method.
Hello, my name is Roni, and this is the second part of our final presentation in petroleum engineering research in topic of machine learning and well-test analysis. My friend Mr. Omundi have already mentioned about the parameters that we need to obtain alpha, lambda, and beta to be able to move on in our machine learning process. He also mentioned that we will use two methods, and the first method was the optimize-minimize method used by a library in Python. The second method that we will be using is an iterative method that was taken from Joseph and Cordis, done in 1983. The idea behind this method is an iterative solution to choose every time a value for lambda, and depending on that value of lambda, we will generate f, g, h, j, k, lm values, and using those values we will find alpha and lambda. So when our g lambda function becomes close to 0 or 0, we can safely say that our alpha, beta, and lambda values are correct. We will keep changing the lambda values depending on the research studies that showed our lambda values are between 0.067 to 0.902. Two iterations has been done. In the first iteration, lambda was chosen as 0.5, and beta and alpha values are as shown. But our g lambda function hasn't been close to 0. The second iteration was 0.1, chosen for lambda. Beta and alpha are as shown, and again our g lambda value is not close to 0. The error that is occurring here is because the model that we are using to calculate P predicted is only for transient solution, but the simulated data is a transient, pseudo-steady state, and steady state. So a further adjustment should be done to be able to account only for the transient part of the equation of the graph and in our flow. A plot of pressure derivative versus time was plotted on a semi-log plot. This plot can help us to see which part of our flow is in the transient flow period and when it deviates from the transient flow period. This will help us to automate the separation process for the transient and pseudo steady state and steady state flow regimes. Before moving on, we want to also double check our simulated pressure and time data. In addition, since our alpha, lambda, and beta values were not identical from both the iterative and optimize methods, we will also check those algorithms and how we obtain those values. After making sure that our values are true and our machine learning model is ready, we will test our machine learning model on actual field data. And then we will try to modify the model for it to work in different scenarios, pseudo steady state flow regimes, for example, or vertical and horizontal wells. Thank you for listening to us, and we'll be glad to answer any questions. And this is our reference list.